Hey, Raj. Morning.
Yeah. Am I audible, right?
Yes, you're audible. Hi, Raj.
Do you have any questions, queries before we, proceed further?
No, I think we discussed everything is very basic. So I thought there were so many terminologies and I go through it's like, yeah, I'm good with those things. Yeah.
Fine. Then. Let me share my screen and then let's start. Let me know once you are able to see my screen.
Yeah.
So we have already discussed all these things. Right? So today we'll be discussing what is Hadoop ecosystem, and we'll just start with Hadoop 1.0, and mostly it was for few years, and then Hadoop 2.0 came, and basically Hadoop 2.0 is still running in some organizations, but now we know that has been mostly replaced by Spark itself. So we'll discuss all those things, right? So if we talk about the Hadoop ecosystem, so basically there are two things as I told you yesterday also. So Hadoop is basically the solution which was given to the problem statement, which is our big data. So big data is a problem statement. So to solve this, this Hadoop system came up. So basically, again, there are two things, like how we are going to do this. Like mainly two things are there. One is storage, another one is the processing. So to get the data into the system, like first to get this storage. So this in Hadoop we have got the HDFS, that is Hadoop Distributed File System. So how that does it work? We'll see it. So basically, to get the data onto the system, at that point of time, mainly there were two tools were there. Apart from one is going to be our through the command line itself. So through command line, we can just generally we give the commands to get the data into the system, or how we are going to read the data into the HDFS. For that, we used to use command line system. Apart from this, there were two more ways. One is Sqoop. Sqoop is SQL operations, you can say. So basically, but Sqoop was only for the to get the data in and out from the Hadoop file system for structured data sets only. Like we are working with tabular formats, Excel files, or JSON formats. Not even for the JSON itself, but yeah, we can also use JSON uh, to get the data in and out for Sqoop. Another tool that we used to use at that point of time was the Flume. Flume is mainly for unstructured data set. So whatever data we are getting the data from the let's say uh, from social media, from sensors, from any of the our data sources from where it is coming. So we can use the Flume, but Flume was only to get the data into the system. We cannot get the data out of the system using Flume, because through Flume we are getting the data in unstructured format. But generally, when our finished data is going to be there, so that is mainly going to be in the form of structured format. Then we can use the Sqoop to get our output. So basically, this three ways. One is going to be by through command line, and Sqoop is for structured data, and Flume was for basically for unstructured data sets. Now we have got different other tools are there to get the data in the system. Now we have got huge number of tools. Like for streaming data, we are having, Kafka is there, Kinesis is there. And for structured data, we have, different ways to get the data into the system. Then my data is going to be stored in the form of Hadoop distributed file system. So as we have already discussed, like it was a, distributed file system is there. So we call it because the system was generated with the person who has, designed it. Although it was all based on the concept of Google file system, how the Google file system is worked. So Google file system was also work in the form of, distributed file system. But the person who coined this term, that's why this Hadoop term coined, and they called this file system as Hadoop distributed file system. So once my data is there in the system, on top of it, now we have got the data. Now we need to, process it. So for processing this, the methodology that was used at that point of time, it was MapReduce framework. So MapReduce framework is, again, it's basically two-way. It is divided into two things. One is map and another one is reduce. So map is basically the you can say the terminology where we are just getting the data, converting into chunks, then doing some processing on top of it, and finally reducing it. So reducing is basically the collection of data from different systems. So basically map is used to distribute the data to whatever the data has been distributed in distributed file system. Map is used to process it on each of the nodes, and then reduce is used to get the data or get the output from all those nodes to process it. So basically MapReduce framework is for processing. So it's the processing methodology that was used. Then on top of it, we can also use HBase. So HBase is basically a known, it's a non-RDBMS. Basically, it's a RDBMS we know, where we are going to process the structured data set. But when it comes to like how we are going to store the data, non-structured data sets, unstructured data sets. So for that, we generally use some data sets. So HBase is one of them. Although there are, you can say, we have got Cassandra, we have got HBase, we have different more MongoDB and all. So different NoSQL databases are there. So these are non-SQL databases which we can use, which are going to store our data sets apart from what we are having as a part of structured data sets. So this is, again, basically most of the non-SQL databases are store their data in the form of columnar formats. My RDBMS stores data in the form of row format. We'll talk about this later also, because we have to understand now most of the the file formats that are optimized file format. If I talk about, they are all column formats are there, which basically store the data in the form of columns. And when we are going to process them, when we are going to access them, so basically those are much faster, as well as in terms of processing as well as the storage.
Okay, this HBase stores within which format you said?
It's in columnar formats, column by column, basically.
Okay.
It shows the data in column formats. So when basically why it is important and why it is because it is storage optimized, as well as it is when it comes to the optimization from the processing perspective, it is also faster. Why? Because let's say I'm storing a in the form of row. So when we are storing in the form of row and when we are accessing it, so generally we have to access it when we are saying select star from table name. So it is used to access all the rows from the table. And even if I'm trying to, let's say, access a few of the columns, so first it has to scan all the rows, and from that row it used to scan a few of the columns out of it. But when we are basically processing on columnar format, so it stores the data like in the name itself, it is storing the name column by column. So when we are accessing the data, so it directly goes to that particular column and fetches the row. It is not going to scan all the rows for that.
Okay, got it.
So both storage as well as processing, both becomes optimized. So that's why, like, if you talk about nowadays, we'll see a lot of this Parquet file format, which is optimized as well as in terms of storage. So let me just give you a live example. In our database YXDB format, there is a format that is used for storing the data. So we were having around a file of 3.3 GBs file in that format. When we have converted that format from YXDB to CSV file, it went to around 18 GB. But when that 18 GB file I have converted to Parquet format, it reduced to 1.5 GBs. So you can think like 18 GBs of file can be reduced to 1.5. So it depends. It's not always going to be there. It depends on how the data has been stored in the original file. Based on that, the data can be compressed. So it's basically a very good file format. In big data world, this file format is getting used. Mostly we are getting used when it comes to the storage part. So we are using this. So on top of it, MapReduce, once we are done with the, so we can also use some sort of tools to get our data processed. So once my data is there in the HDFS, so those who are basically this MapReduce technology was like how you are going to doing the code. So in MapReduce originally was used to write the code in Java, but then it also supported two more languages, that is Python and R, and now we have got SQL also. So but this Hadoop doesn't support directly SQL, but now we have got framework which uses R. So basically for users, basically at that point of time where this Hadoop was introduced, so most of the people who were working from the in data world, they were mainly from the SQL background, right?
Mm-hmm.
So they were facing a lot of issues in when they have to move from SQL to MapReduce. So it was a little bit difficult for them to adapt to this MapReduce technology. So that's why engineers have developed this another system which is called Hive data warehouse system. So Hive is again similar to the SQL language, which stores the data, and when we have to process it, so we can directly query SQL like queries. Although there was little difference between Hive syntax and the SQL syntax, but if you overall see, it was almost 19 to 95% similar to what we were doing as a part of SQL queries. Then another at that point of time there was another language which is called Pig Latin. It is mainly used for data analysis. So this language was exactly similar to what we used to write these statements in the SQL itself. But in background, what was happening, because these all technologies were developed on top of MapReduce. So whatever we were doing, so everything was getting converted into MapReduce, because Hadoop only understands when it comes to the story, Hadoop distributed file system, and when it comes to the processing, it only understands MapReduce. So everything was getting converted into MapReduce. So just that conversion from either we are doing it through Hive or Pig Latin, or Mahout. Mahout was at that point of time, we have got the machine learning library was there. So just to, if somebody has to do some sort of machine learning task, so they used to use this code in this Mahout learning library. And top of it, there was another tool which was given by Apache, which is Apache Uzi. So Uzi was just a workflow which was used to orchestrate everything, so that when it comes to designing the or running the jobs, so for that we were using Apache. So Apache was like it was a workflow to orchestrate everything in one framework itself. So this was like how the Hadoop 1.0 used to work, right? Any question is in a 1.0? Because if you understand 1.0, we have got just one difference between 1.0 and 2.0 with some new other frameworks.
Raj,
Understand?
can you please explain the mapper and the reducer framework? Exactly the work.
Yeah,
Exactly.
MapReduce will see in I'll show you with one diagram, right? How it actually works. So map is basically what is like wherever my data is going to be there. Hadoop distribute like MapReduce is the processing framework. So for processing, what I need, like processing is going to be done on some sort of data. So my data is distributed across multiple machines. So what MapReduce is to MapReduce is basically going. We used to send the code, or we can say the MapReduce on each of the node, and there the processing is going to happen. So map is basically it's a distribution of my data was distributed. So on each node my data is going to be processed, and then reduce is just to combine that result. So map is processing the data on each of the node, and reduce is basically reducing. The reduce means it's basically the collection of whatever the output we got. I'll show you with the help of one diagram, right? How it works.
Yeah, okay.
Okay, so this was Hadoop 1.0. Now in Hadoop 1.0 and 1.2.0, there is one difference. If you can see on top of HDFS and MapReduce, we have got one more introduced, which is called Yarn. So Yarn is yet another resource negotiator. So this was the resource management, cluster resource management. So basically, MapReduce in Hadoop 1.0, what it was doing is like, as we are working on, we are not working on a single machine. We are working on a cluster of machines. There are multiple machines because my data is distributed across multiple machines, and we are sending the compute in the sense MapReduce to each of the node, and we are processing it. So in Hadoop 1.0, MapReduce was doing all the task of even it was doing the resource management also. So sometimes what happens is like it has to do three tasks. One is like basically doing the processing. Then also it has to do this resource management. But sometimes what happens is like it was doing MapReduce and this cluster management thing. So it was observed that when they were working on a smaller cluster, let's say 100 to 200, 200,000, 2,000 nodes of cluster, even 4,000 nodes of cluster, it was working fine. But when we were moving beyond 4,000 nodes, there was some lacks that they found in terms of performance in Hadoop 1.0. Because at that point of time, they find it out this MapReduce was getting overburdened with this huge task like cluster management. So they have come up with another technology, which is Yarn. So Yarn is yet another resource negotiator. It's a cluster resource management which used to do the resource management. So the two tasks which were, the resource management and, within resource management, basically we have got two: master resource management and at the node management. So those two tasks were taken up by the cluster resource management, and the only task of my MapReduce framework is to process the data. Like in Hadoop 1.0, apart from processing, it was doing the cluster management also. But in Hadoop 2.0, to reduce this burden from the MapReduce, they have come up with Yarn. So now the Yarn is doing the resource management, and the only task of the MapReduce is to process it, right? So once they have, introduced this Yarn, they were able to, process it up to, they have tested at that point of time, they have tested it for, 12,000 node cluster. Till 12,000 node cluster, there was no issue at that point of time. So I'm talking about around 2006, not at that, because at that point of time, 12,000 node cluster was a huge thing. Nowadays, we are having around 20,000, 25,000 node clusters are also there. And those are, even more than that, based on the, requirements like Amazon or Google, they even they are having very huge clusters are there that they are using for processing their data sets, and the rest of the things are all same. But
Hadoop is, Raj, Hadoop is still the organizations are using that.
Hadoop is mainly getting used in background for the storage purpose. Like when it comes to, and yeah, there are some organizations are there, those basically in background they are running it. But for processing, now we are not using MapReduce, but the terminology is MapReduce. We have moved to Spark, right?
Okay.
Because Spark is almost 10 to 100 times faster than MapReduce, and how it is faster, we'll see, right?
Prior to that, would it be possible? Can you please explain the node cluster? Okay, how that system will get work and how data will
I'll come to
process?
that. I'll come to that part. I'll come to that part. I'll
Yeah.
just now I'm just giving you based on this, like the basically picture, like what is how the Hadoop ecosystem look like. So we have got the image. Okay, we have got this. We have got different tools to get the data. Then data is distributed across multiple systems in the form of HDFS. Then on top of it, we have got Yarn, and then likewise, I'm just giving you a brief about these things. But I'll tell you like how basically this Hadoop distributed file system works and how this MapReduce works. That is going to be to understand the framework. These two things are necessary, and the rest of the things basically those are the tools that we use on top of it to get the data, right? Then there were other tools apart from this what we have as a part of Hadoop 1.0. There was some framework at that point of time, that is MPI, that is message passing interface. So basically message passing is like whenever somebody has to work on messages, so for that they have built a new API. So and somebody has to work on the graph forms, like wherever the companies which are working in terms of networking and all, so or social medias, they generally used to have this graph. Previous to these frameworks, they used to do this thing in the form of MapReduce only on top of it. So when they come up with NPI graph, so they can directly use these APIs to reduce their coding part, processing part. It got reduced because of they were having already APIs built for that. So just call that API and we were able to use those things, right? So this was all about like how the whole Hadoop ecosystem looks like, right? So any questions, any queries so far?
Is there any another version Hadoop? Hadoop 2.0 is the latest one, or any another version as well?
No, after 2.0, 3.0 is also come, but that was not, got so much famous. There was only or mainly the difference between 2.0 and 3.0 was related to the optimized version of Hadoop only. Otherwise, the rest of the things in Hadoop 3.0, it's almost the same. But when Hadoop 3.0 came, before that, basically, Spark came and Spark took over Hadoop itself. So that's why most of the organizations they basically when the Spark came, so it was faster, but in terms of cost, it was little costlier when it to differentiate between Hadoop and Spark. So at that point of time, most of the organizations which were able to adapt that, they don't have any issues with the cost itself, so they moved to Spark itself. But today, what happens is like the use of this has reduced a lot. There's a lot of noises coming from your side. Okay, so what I was saying is like the use of Spark has increased, and the use of Hadoop has reduced a lot because of
I think Spark was real-time data processing.
no like for even we can do the real time at that point of time. Hadoop is mainly for yes. When it was introduced, it was mainly for the batch processing itself. When Spark had introduced, so it was used to do the batch as well as streaming data. But for streaming data also in Hadoop, we use this Flume, right? So Flume is to get the data, not exactly the real time, but we used to get the near to real time updates. But when the Spark introduced, as it basically, so the main difference between Hadoop and Spark is the processing part, right? MapReduce works, or basically process the data in the form of on the disk itself, on the storage part, right? Because we are sending the data to the onto all the nodes where my data is stored, and then we were processing it. Once my data is processed, we used to get the data to our driver node. This is what we used to happen in as a part of Hadoop. But in Spark, what we are doing is like we are processing in the memory itself, and because of this processing in memory itself, so even if we are processing on the disk itself, it is almost 10 times faster. But when the data size is small and we have got huge cluster is there, so we are able to process the in memory data itself in the form of RAM, and finally we are just reading the data from the RAM, from the disk in from the nodes, and then when we are finally writing the data, at this point of time, only the reading and writing is happening. But in MapReduce, there were a lot of read-write operations happen, and because of this, Hadoop was is little slower when we are going to compare it to the Spark itself. But in Spark, everything, once we have read the data, all the processings are going to happen in the RAM itself, in the memory itself, and finally we are writing the result. So in this way, it was almost 10 to 100 times faster from this was basically the tested part.
So this Hadoop is completely replaces the Spark replaces the Hadoop completely or part of it. So as you said, the MapReduce has been replaced by Spark now. So Hadoop is using many companies. Hadoop is using as a background. So
some companies they are using it for storage purpose only. That is Hadoop distributed file system. Like the data is going to be stored on HDFS, and on top of Hadoop distributed file system, there are more file systems has been created, and those are getting used now. But if you see on the background, HDFS is it's still getting used, but like Yarn, MapReduce, these has been replaced by the Spark itself. But still, for cluster management, Yarn is still getting used. right? In background, we are still using Yarn for cluster management and all. MapReduce is definitely.
So Yarn is used in the sense the Hadoop 2.0 or 3. You said that
Yeah,
was 3.0.
it was there in 2.0, 3.0, and now in latest technology also, Yarn is getting used for cluster management in background itself.
Oh no, my question is currently companies using 2.0, the Yarn cluster
Yeah, it's
2.0 or
like if somebody is using, like as I told you, most of the organizations, they are not using MapReduce at all. So Hadoop is getting used, Hadoop 2.0 is getting used, but mainly for the storage purpose. This is what the companies are doing, right?
okay.
So clear till here?
When we are talking about Spark, you were saying this thing exactly. There was a some memory sort of thing, RAM kind of thing.
Right.
RAM is common for all the nodes, or it it has a separate RAM for the all of the nodes.
Okay. No. Within the like, if you are talking about a cluster, so generally we used to have the similar nodes, like similar configuration nodes on all the clusters. So, like if I'm having 100 node cluster, so if I'm using, let's say, 8 or 16 GB RAM, so it should be same on the on that particular cluster. Like if I'm introducing a new cluster at all, so definitely I can increase on that system, right?
Means you want to say this thing exactly. We have a 100 node cluster, so there is a single RAM can work on that.
No. Each system is going to have, let's say I'm having a 100 node cluster. So 100 nodes, let's say I'm having 12 GB, 8 GBs RAM on one machine. I'm talking about, and let's say storage is 2 terabytes on each machine. So this
Hmm.
this kind of system is you see it's a very general purpose cluster. It's a commodity machine. So
Hmm.
we are having the same configuration system, 100 nodes are going to be there, right?
Yeah.
And then on top of it, we are going to have one machine, which is going to be my master node. So basically, we'll come to the architecture part. So in the architecture itself, we will be able to understand it's a slave master slave architecture is there. Let me come here. Like, so basically, these are the core components that we are talking about. So two things are there. One is my storage, another one is the processing. So for storage, we are going to use HDFS, and for processing, we are going to use Yarn, because now we are moved to processing part. So within this, we are having different daemons are there. Daemons basically are the the processes which are running in background. So for storage, we have got name node and data node. So name node is the master machine and runs on the master machine, and data node is basically my the slave machines, or the actual cluster where everything is running. And apart from this, we are having the concept of secondary name node also. I'll tell you what it is. And then we have got Yarn, as
Yes,
I told you.
we will move on to that name node and cluster node. The thing is this, my question was is, okay, we are using the separate RAM memory for each node, or we
Yeah,
have.
yeah, this is like, as I told you earlier, I think last session I also told this thing. Like in basically there were two storage ways we can store access it. It's scale out and scale in mechanism. So scale in, what we can do is, like, scale in, we can increase the RAM or storage on a particular machine, but that is having some sort of limitations. As I given the example of the phone itself, I can increase the memory to double x, triple x, whatever I'm having right now, and RAM also, but after certain point of time it cannot be done, as its chipset is not going to work. So similar way, in each node, whatever the the RAM and storage we are having as a part of our node, we can increase it in up to a certain level in vertical storage, vertical scaling medium. But in scale out or scale horizontal, we are not basically increasing the RAM. We are basically adding the more number of resources. So basically, we are adding more number of machines to the cluster. Let's say initially I've started with 10. Then if I need, I can add 2 more machines. I can add 10 more machines. I can add 100 or more machines. I can add 1,000 more machines. So there is no, uh, you know, uh, there is no limit on that part. So yeah, when we are basically uh, for your personal use, that is fine. But if when it comes to when we are creating the cluster, so it is always better to have the same configuration on all the nodes. Am I able to answer your query?
Yeah, it's clear now.
Yeah. So let's say, as I told you, like we are having 100 node cluster. So on the 100 nodes, if I'm having let's say 8 GB RAM on one machine, so on 100 machines we should have. Otherwise, like it's not mandatory. If I am having let's say on out of 100 machines, if I am having on 80 machines, I'm having 8 GB RAM, and on 20, I have added 20 new machines, and I have having let's say 12 GB RAM. So that is also fine. It's not the case that you cannot do it. We can have that that part also. But generally, like for uniformity, we generally used to have this kind of clusters, because I have worked on 100, 200, even 300 node clusters. So there, I have never seen such things like we are having, let's say, uh, 20 node cluster, 100, 200 node clusters are there. So those are all having the similar configurations. But nowadays, you don't need to think about these things at all, because we are mainly working on the on the cloud itself. So they are providing us these machines. They are providing us the storage as well as processing. The only thing is how we are going to utilize them, right? So although we
That's
have
why
to
my
understand.
question was. That's why my question was. This thing exactly. Hadoop is still going, still using organization, or everything is moved on to the cloud itself.
If I talk about 95 to more than 95% organizations, they have already moved to the cloud, because you know the organizations, only those who wants to keep their data safe, they even don't want to expose it to any of the cloud. So based on their priority requirement, they are doing it. But yeah, as I told you, when it comes to the data which they can expose easily, and even for the cloud providers, there are a lot of different basically contracts has to made based on your how much data, your sensitive data it is. So based on that, they are doing it. So different contracts have based on the security reasons, it will go. But sometimes it's still, if it comes to some government data which should not be exposed, they are using their own clusters. They have built their own clusters, and they are using it. But yeah, if in general you will ask, so definitely it has been reduced, or we can say it's got eliminated, right? Because right now, from the last I think 8 to 10 years, uh, I'm seeing, like, there is a huge drift from from Hadoop to the cloud itself. So most of the organizations, if new organizations, they are also coming, they are all using this cloud, because nobody wants to take this headache again, because managing these large clusters is a big deal, right? So why I'm going to do that? I have to focus on processing the things, instead of processing what I have to do. And for to get that processing to storage my data, why I should worry about that when somebody is providing me that thing on a very cheaper rate, right? Because I'm just renting them. So just owning a home and renting it, you can just, this is the same scenario that the clouds are providing, right? So we are just renting the things. Although in long run, when companies know that okay, they have to use these their clusters for their own use for the their, based on the usage, if they want, they can even create their own data centers itself. But now this scenario has reduced a lot. Most of the organizations, they have moved from their even from their private uh, clusters to the cloud itself, because managing them and getting the new data every day, new requirements are coming. So just handling all those things need a lot of money, lot of efforts, lot of staff is required, lot of space is required. So those things are reduced by these cloud providers, and for that they are charging the money. But if in initial when you see, so definitely it's quite cheaper owning a house or just renting a house. You can see the difference. So similar way the organizations are doing in this way, right?
One question out of the box. Do India have any of their own cloud?
uh, this is like it's not basically they have their own clouds, but I'm not sure on that part, because most of the things that we are using it, maybe government has their own, clouds are there. But what we are seeing right now, it's not like that. Everything is, you know, it's
Everything. These three or four clouds are there only.
no,
Google,
yeah, these
AWS.
yeah, these are the main ones. But if you talk about, like, we have the cloud for Oracle, we have the cloud for other organizations also. Like, mainly if you talk about the organizations which uh, which were which are there in data side quite long time. So those who have already started working on this part, so they are having their own cloud itself. And like, even if you want, they're now we have got the concept of creating their own private cloud itself. So you can do that. But the only thing is, like, definitely for cloud is what is cloud? It's again a data center, right?
It's a data center. It's a server.
Yeah, yeah, it's a data center, that's it. So those who have already worked, like, these organizations have thought a lot about it. They build their own systems. So yeah.
we
Okay.
can. Hmm.
Yeah. So basically, if we talk about the components, so for storage we have got two main components. For processing we have got two main components. So masters are there, and then we have got the slaves. Slaves we are called as data nodes. So basically, it's all master slave architecture is there. So name node is there as a part of Hadoop distributed file system, and for processing we are using this resource manager. And then data node is there, where the actual processing is going to happen. So name node, you can think about here it as a you can say it's a project manager, right? Who is having a lot of projects, under whom we are having a lot of let's say leads are there, and then within leads we are having the junior developers are there who are actually doing the processing. So similar way, this for resource manager and node manager is there. So resource manager, you can think as your manager. Within that manager, there some leads are there, and then leads are within each lead. The data is getting processed on each of the data nodes. So here, if you see, master can they can talk to each other. Node manager and data node, which are at the slave side, they can talk to each other, but their cross communication is not allowed. So name node cannot talk to node manager. Resource manager cannot have any communication with the data node. But my HDFS, slave and master, they can talk to each other. My name node can talk to data node. My resource manager can talk to node manager. Understood? This concept is quite easy, right? Within the same HDFS, master and slave, they can talk to each other. Processing, master and slave can talk to each other. both storage and processing, masters can talk to each other, slaves can talk to each other, but their cross communication is not allowed, right? So my name node cannot talk to node manager, data node cannot talk to resource manager. Till this point, it's clear?
Yeah, clear.
Yes.
Yeah. Okay, thank you. So this is how it works basically. So for storage, we are having the name node as the master, which is connecting to each of the data node. So whenever, let's say, a file is coming, let's say some, I just given some, file for the storage part. First, I'm going to store the data. So let's say my 1 GB file is there. So the default, size on HDFS, the file size is going to be, or the you say the chunk in which my file is going to be divided on HDFS is 128 MB. Again, this is configurable, but this is the default size for Hadoop 2.0. And right now also, as we are using, this is the default one. Why? Because we are still, for storage, as I told you in background, we are still using HDFS. So by default, the size is going to be break and going to be stored onto different nodes in this size only. But again, if we want to make it 256 GB, so we can make it in acts of 128 MB. But in Hadoop, 1.0, it was 64 MB. So again, taking this, the concept of, if we are having, very small files are going to be there. So those also creates a lot of issues when we are processing it. So nowadays, this question is a lot of time asked, like, what is the small file problem and all. So how that is going to be resolved in current technology, that is also used, like in Databricks, we have got multiple ways through how we are going to deal with it. So this is just to avoid that, they have bring up from 64 MB to 128 MB, because if we are having more number of files are there, so we have to store more metadata for that. And like navigating to different files is again going to be problem, because here we are not going to talk about one, let's say 1 GB file or 2 GB file. When the file is going to be data is in the form of terabytes or petabytes, so just dividing it into 64 MB and dividing it into 124 MB, it's totally going to, let's say, 100 to 200 files, so double the size. So when we are doing it in the form of terabytes or petabytes, so it's going to be in millions of the file chunks will be there, and their metadata is going to be doubled based on that. So that's why, keeping this file, they have just bring it to 128 MB, and this was very optimal in terms of processing as well as storage. But yeah, if you want, you can just do it. You can increase or decrease it. Same way, like resource manager is the one who is going to process. So on each of the data node, basically on the slave, we are having these two them as node manager and data node is running. So for the storage, it's we are calling it as data node, and for processing it, we call it as node manager. So on each of the slave node, we are going to have this data manager. So this is the one who is responsible for processing all the tasks on this particular data node. Second one, this node manager, let's say node manager 2, is responsible for working on this node 2. So this way the Hadoop processing works. So just to recall this, it's as name node is the master of my system, and the main system who is coordinating at the top. So basically, you can say here name node, you can take it as the the, let's say, the CEO of the organization. Just to remind. So generally, in one organization, we are going to have just one CEO, and within each CEO, we are going to have a lot of peoples are there in terms of the employees. So one person is managing the whole organization. So the person name node is going to be that person who is managing it, it's going to be expensive. So here, when it comes to storage and processing, so basically this name node stores all the metadata, and it handles all the metadata. So when a file comes for the storage part, so it will come to the name node. Let's say I have to store 1 terabyte of data on my cluster, so I'll go to the name node and say, okay, this is my file and I want to store it. So this name node is going to check on all the data nodes, like, okay, I have got, let's say these 100 node cluster, these are the 50 machines on which I can put my data. So this is how it works, right? So this is the task of the name node, because name node knows everything about the cluster itself, like how many data nodes are available on each data node, how much data I can store on a single, like how many chunks of data we can put on one node, and how we are going to the replication and all. So those kind of, like, everything about the data nodes, it's stored in the metadata, and that metadata is with name node itself. But the actual story is going to happen on the data node. So same way, basically it's which is actually providing the actual storage, because my name node only stores the metadata. So if I talk about the storage part on this, like what is going to be the storage, so name node doesn't have that much amount of, or that it doesn't need that much amount of storage part. So generally you can have around let's say 1 TB or 2 TB of storage on one name node part, but it should have all the data present or metadata present in the RAM itself for processing itself. So on name node we are having, it's a high-end machine which is having around, let's say, minimum 512 GBs of RAM. So it can process it. So name node generally used to have huge like RAM. In terms of RAM, it should have, because it can store the data. Let's say for a typical cluster, we can have around 120 GBs of RAM on a 100 node cluster, and the data node can have around 8 to 12 GBs of RAM on. But the storage part, let's say name node is having around 2 TBs, but my data node can have around 8 to 10 or 12 terabytes of storage on each machine. So this is how it happens. So in data nodes, basically the storage is going to be the like we should have the more storage part, but for processing we are going to process it through the processing it in the parallel itself. So, and we are not processing it from the same machine. So if I am having, let's say, 128 GB on name node, and on cluster we are having a 100 node cluster, and we are having, let's say, on each machine, let's say 12 GBs of RAM is there. So 100 into 12, so we are having around 1200 GBs of RAM for processing itself. So we have to store, we have to process from the data node itself. So on a single machine, it's going to be a commodity hardware, but from the storage and processing perspective, as it is storing on multiple machines and processing in parallel, so similar way, it becomes quite faster as compared to when it is going to process from a dedicated hardware or server itself. So that's why it reduces processing time a lot, or it basically reduces, like, whatever process we are doing, let's say in hours, or in sometimes it took around full day to process. The Hadoop can do it in few hours. But the same thing when it comes to Spark, it can do the same thing in few minutes also, right? So this is how it does. So again, name node, what it is going to store, as I told you, it mainly stores the metadata, and it is going to be in the main memory. So that's why we need to have it the larger RAM size on the name node itself. So basically, why we need it, like so if you have got the idea like how it searches. So let's say this kind of data we are having as a metadata, like, okay, in this folder on these 135 machines, they have got their, like in the cluster itself, they have got their unique machine configurations are there, which the name node stores. But here for understanding, we have just took it as 1, 2, 3, 4, 5. So in this folder, for this hinfo file, the file has been stored on 1, 3, and 5. For P details, the file has been stored on machine 2 and 4. Likewise, like it stores the data in this format. So it can track it like, okay, when I just ask them to, let's say, my 1 terabyte of data is going to be stored on which machines. So it is going to check by the name node, like, okay, these are the machines on which we can put this data and in these number of files. And then they also used to store their replicas. Okay, what all files are going to be there. If 3 replications are there, so these replications are going to be there on which machines. So that metadata is stored in name node itself. And why we are storing them in the main memory itself? Because we don't want that there should be, no demand for paging. Paging means like paging happens, if you remember, this concept is like whenever we are, trying to access anything, if that is in the RAM itself, so you will get to know at the runtime itself. But when that page is not in the main memory, then it goes to search in the hard disk itself, and then search for that file. Okay, this file is there. So this is called demand paging. So when we are demanding something and that is not there as a part of main memory, then it is go and searches it in the system itself and then bring back the data. So we don't want that data to be on demand, or this should. So that's why we are having, main memory means RAM is more in name node. So generally we used to find like what is the list of files, what are the blocks on each file, then what are the list of data nodes for each block, file attributes, access time, replication. So they are all the attributes which are related to the metadata itself. Those are going to be part of my main memory, and also records for creations, deletions, whatever, what transaction loss, like what we did with the file itself. If my file has been deleted, updated, at what time it was created. So if we don't need it, it got deleted. So those kind of information, it getting used by the name node itself. So as I told you, in Hadoop 2.0, basically the default file block size was 128 MB, but in Hadoop it was 64 MB. So why they have did it? So as I told you, the main reason for HDFS block size is to reduce the cost of seek time, because if we are having more number of blocks are there. So definitely when it comes to the getting the file, searching the location for this, it will take time. But when we are having, let's say just for example, 200 MB file in 64, we are having 4 blocks in Hadoop 2.0 with 28 MB, we are just having 2 blocks. So searching in 2 blocks and searching in 4 blocks, definitely 2 blocks is going to be easier. And also, as I told you, like when it comes to the name node itself, in Hadoop 1.0, the name node has to store the metadata for these 4 blocks, but in Hadoop 2.0, it has to store for just for this ab.txt file, just 2 blocks of metadata. But so it is just an example, but when it comes to terabytes, petabytes of data, so you can imagine. So to limit, and we have got the limit considerations on the size of the RAM on the name node itself, because if we are going to have increase the RAM on the name node, again it will bring the cost. So instead of every time adding the cost, what we can do is, when we have got the this facility with us, then we can change the configuration of the file. Instead of even 128 MB, if we want, we can make it to 256 MB itself. It's going to be every time 128 MB multiplied to or by 2x. We can do this way. So these were the main, then they have come up with, okay, 128 MB is optimal in terms of, both reducing size, seek time, as well as, considering the memory constraints on the name node itself. So it was, decided. So now also, if you go, so by default, still we are having this 128 MB as the, block size. Like even if I'm storing my file, even on the, on any of the cloud itself, if you see and go and check your, file block size, so it is by default 128 MB. Clear? So now we'll see like how the replication is going to work on each, the part. So basically, in on the data center, we have got this, a rack policy. So rack is basically, it's a, as we have got the shoe racks, right? Similar way, we have got the racks. If you have ever seen, the data center, so we have got different racks. Within these racks, these machines are there. So machines means like there we are not having any of the, the monitor itself. It's basically the only the, the CPU. So CPU contains both my storage as well as processing, right? So this is what we are having as a part of, rack. So in the different racks, we have got, machines has been added, connected to the network. So how many machines are going to be there as a part of the cluster? So we can have a different number of racks can be there. And these racks can be there on the same data center, or they can be at the, different locations. All three can be on the same. Two can be on the same. Three can third one on the another, or based on the, the security, we can have like rack 1 on one location, rack 2 on another location, rack 2 on another location. This is just an example. This way we can just, choose, but based on like how we are going to choose it, it basically again going to put the cost. Like if we are just having running all the three, replicas on the same data center, so the cost is going to be reduced, because when we are going from rack 1 to rack 2 to rack 3, so we are just, the lot very minimal, network is required, because we are just copying in the same data center itself. But when it goes to the different locations, so we are just moving the data to different locations. So there again the transition cost is going to be get introduced, and those kind of things are based on the requirement itself. So let's suppose we for a particular file we have got 3 blocks are there, A, B, and C. So how we are going to store that? So there are different replication policies. We are taking it here it as one only, 3 by default replication policy. Like we are going to store file A, and how we are going to store on different racks. So let's say I have stored block A on rack 1, then its replications I have stored on rack 2, not on rack 3. So this is one way that I'm going to store. So what it does is like basically this first, when we have just copied this first block of data, then its replication is going to be happen on 2 more nodes. So these 12, it's a node. So you can take, we have got a 12 node cluster, right? So these 2 replications are going to be there on 5 and 6. Then let's say block B, we have stored original block, we have stored on machine 6, and its replications are going to be there on next 2 machines. So again on another rack, not on the same rack. And the same is going for this one. So this is one way. But if we want, like for let's say block A, we can have one on rack 1, one on rack 2, and this, instead of having this 6th on 6th one, we can have it on 9th, machine 9, right? So this way we can also do it, but it will again require some sort of network, because within the same rack If we are copying the data from 5 to 6, it is minimal, efforts are going to be required. But when we are, moving from 6 to 9, let's say, for block A. So again, whatever the efforts required from rec 1 to rec 2 and then rec 2 to rec 3. So that sort of, efforts are going to be done by the network itself. So based on the requirement, as I told you, rec 1, 2, and 3, they can be at the same location, or it can be like rec 1 and 2 are on the same location, rec 3 on different, or rec 1 on one location, rec 2 and rec 3 on another location. All three can be on 3 different locations. So based on the, how you want to save your data, the cost is also involved, right? And why we are doing this, let's say at some point of time, why we are not storing all the data in the same rack? We can do that. But the thing is, like, if something happened with the rack 1, so for that point of time, let's say some downtime is there, something is there, so I won't be able to access my data. But let's say for some point of time, if my data is distributed across different racks, so if my rack 1 is down, I can get the data from rack 2, right? Similar way we can, so your machine is not going to be down, or you are able to access your data. It is available all the time. It's not down for any point of time. This is how.
What happens if rack 1 and rack 2 both failures?
Yes, this is what I was trying to say. So generally it is not going to happen, because there might be the case like if you are using rack 1 and rack 2, if they are on the same location and if something happens to the whole data center, then definitely for that point of time, your data won't be available. But yeah, that's why I'm saying, like, for security, it's you have to consider this thing based on your requirement. If you know that, okay, you need to have your data availability 100% 24/7, and definitely you can go for the rack 3 concepts, like the replica is going to be having different racks, and these racks are not on the same data center. So definitely, let's say generally we used to have the data replicated to we have got different availability zones are there. Even if you are let me give you the example. If you are working on the cloud infrastructure itself, so when we ask for the cloud, like where my data is going to be reside, so they ask for, okay, which zone you want, which availability zone you need. So we have to choose our availability zone on our basis. So even for my data right now, we are having replications at 3 different locations. So sometimes what happens is, when I'm trying to reach out to get the data from one location, which was near to mine. So first time we always try to access it from the nearest location. So we have got, let's say, my data center is in South Asia. I'm giving you the real-time example for my project. But for my US clients, they have got their data replication, because we have got 3 locations are there. One is South Asia, another one is Europe, and another one is in the US. So the peoples who are near to US, and so for them it's going to be US. For Europeans, that is going to be there. But sometimes what happens is, like, I am not able to access the data from my availability zone, and I need it. So what I can do is, I can change my availability zone and go to the Europe one. Although it will take some more time in the sense, because now the distance has been increased from Southeast Asia to Europe. But still, I'm
What's the reason to distribute into the different countries, not in the same country for the 3 different locations?
yeah, that's why I'm telling you, like, based on your requirements, it has been done like that, because
No,
now
but they
operation.
did, your organization or whatever the client is there, they chosen these 3 locations into 3 different countries. Why not in single country?
Yeah, because even if they are choosing it for the single country and single data center, they can do it. But now their operations are in different countries. So based on your requirement, as I told you, like if you are a very small organization and you have that, okay, just because it is when you are going to store your data onto different locations, so it will bring a lot of cost. But to be more secure, generally, even the organizations who are dealing with, they are having their clients, and the client has asked them that we want our data to be available 24/7. So for those reasons, they have to do it. They have to take it. Like, let's suppose my Southeast Asia uh, data center is down for some reason. There could be any reasons, right? Power failure or whatever it is going to be there, because they have to maintain uh, for running a data center itself. There are a lot of constraints are there, and if some of the constraints are failing there, so there might be some issue. Like uh, in India, we have got the data centers in Mumbai itself. Most of the data centers we are having in Mumbai. So sometimes it happens, okay, some of the data centers are down for some time. So if there's some critical data is there, some sort of criticality is happening, and your data center is there and your data was there on just one location, so definitely for that point of time, till the time the data center is not up, you will not be able to access your data, right? So keeping these constraints in mind, it they generally, like every organization, not I'm not saying every, but yeah, most of the organizations, they used to have their racks available in at least at two location, and at least at two data centers. Maybe they can be in the same country, but yeah, depending on the uh, you know uh, availability and their feasibility, they can have it into different ones. Like, even let me give you one of the organization in Japan. They are having their data at 5 different locations also. So it's all based on the criticality of the data, because once the tsunami was there in Japan, so there were even some data centers that they lost at that during that tsunami. So a lot of other organizations have learned a lesson from that, and now a lot of organizations, they have storing their data at different locations. Let's say if something such incident happened, natural calamities can be there at any point of time, and if something goes down, so during that period, that data center was down, and even a lot of things happened. Even some of their nuclear power plants got destroyed during that tsunami. So how much destruction that has been done. So keeping all those things in mind, now the organizations have adapted this. Okay, instead of keeping this thing at one location, we can have it in multiple locations, even in multiple countries, multiple regions are there. So yeah, but always first priority always goes to the the nearest availability zone, so that you should be able to access your data very fast, right? So again, this question is, it's based on the requirement. It's not that everybody can choose automatically. It's not that easy. It's based on the requirements. What like how you want that data to be accessed, and like if in terms of like in the times of any sort of such issues, how you are going to, like, how, what is the criticality of your data is there. Like if you are able to manage, like, okay, if for some point of time, if my data, I'm not able to access my data, and that is fine. So yeah, why we should go for the even for different availability zones, we can have the data at our the nearest location. But now they are quite safe, so it's not like it's going to happen on very frequently. But this is how it happens, right? Understood? Okay. So now this is how my read and write operations takes place. So as I told you, basically name node, whenever how it happens, like I have to when I have to read the data. So how I'm going to read the data? My file is already there on the let's say on HDFS. So when I'm asking to read the data, so I'll go to the name node and I'll say, okay, I just want to read this file. So the name node, what the name node will do, basically it will go to the to the name node first, because client wants to read some data. So for that, I'm just going to say, okay, let's say I've given some command. I wanted to read this file. So I've given for reading that file, I've given some command. So it will go to the name node, and basically the name node is going to ask this thing from the resource manager, and asking this, okay, what is the location for this particular file? Then name node gives this file location first to the resource manager, and resource manager will come back to the node manager and ask, okay, this file is existing on these files. Then the node manager goes to those data nodes and read that file and bring data back to the HDFS client. So this is how we read the data. Same way we also write the data. So when we are going to write the data, the client wants to say, okay, I've got 1 GB of file. I want to write it to the cluster itself. So first it will go to the name node. Name node gets the metadata, because name node know, okay, these are going to be the machines or the data nodes on which we have got the availability of the nodes blocks are there where we can write that data. So that data goes to back to the client, and then clients directly interact with those name nodes through node manager, and then it writes the data to those files. But name node only gives data for the for the original write of the data. Let's say I have got 1 GB of file is there, so 8 blocks are going to be there. So name node gives the location for those 8 machines where we can store the data. Then each data node can connect to each other, so they know what are its neighbors. So they try to write the replica to its neighbors itself, right? This is how it generally happens, right? So that the process becomes faster. And then in this way, we generally used to write the data, right? This is how the read and write operations happens. So now, if I talk about the Hadoop distributor, so initially it was the cloud era, which brings this Hadoop concept, but later Hortonworks and MapR, they have also contributed to it. But the major part, or the major Hadoop share, was done by the cloud era itself. Till the time the Hadoop was so more than 60% of was under this cloud era itself. Then Hortonworks and then MapR. So these 3 distributions of Hadoop are there. So yeah. So these basically gives you a like if you want to go and if you want to set up your own Hadoop distribution, you can do it. But these are the the companies which are already going to provide you the distribution files. So within this, everything has been like you will get the HDFS, you will get the MapReduce. On top of it, then you are going to connect to your clusters itself. There you need to specify everything in your config files. So everything is going to be part of config files, like what is going to be my replication factor, what is going to be my file size, how I'm going to process it. So those what is going to be in processing, like whether I have to use yarn, where and which application I have to use, how we are going to utilize it. Those kind of information is going to be part of our core component configuration files, and how we are doing those configurations. Based on that, my Hadoop actually works. Okay, so any questions, any queries so far? Please let me know. Whatever we have discussed so far, like any of the questions, queries. Shamila?
No, Raj, I'm good.
Okay, fine. So this is, we have already discussed. So this is how a typical cluster looks like. Just so basically we have got active name node is there, let's say, which is having RAM of 64 GB, hard disk is having 1 terabytes, and some processor configurations are there. But at the data node, you see we have got 16 GB RAM, and hard disks are 6 into 2 terabytes. So here we are just having 1 terabyte on the name node, but we are having large storage on the data node itself, because these are the ones who are going to store the large amount of data. Yes, so that's why data nodes are the actual nodes, and these are commodity hardwares. So with the help of active node, we are also having the concept of secondary name node. But secondary name node, you can have the similar configuration or lower configuration. So when this the concept of secondary name node comes, so basically this concept was there in Hadoop 1.0 also, the concept of secondary name node. So as we have discussed, like name node is a high-end architecture. It is very it's quite rare that this name node is going to be down, but we know that, right? Although it's a high-end machine, but even servers are prone to down. So what is going to happen is, like in case of active name node, if my active name node is down, then what is going to happen? So if master is down, my master node is down, then my cluster is down, right? I won't be able to access anything, even though all data nodes are working fine. But I don't know like how it is working, because if my name node is not there, I won't be able to see anything, because my metadata is with name node. So like what is happening on the data node itself, what processing it is happening in background, but what it is happening at the runtime, we'll never get to know this. And this information is not going to be with the name node itself, because my name node is down. Then how can I get that? So for that reason, we have come up with the secondary name node. So like in case whenever an active name node is down, then we can switch over to secondary name node. And how it is going to switching is going to happen, that is done at the at the orchestration level. Automatically it is going to be moved to secondary name node, because we are having Zookeeper, which is a top level daemon. Basically it's a orchestrator which takes care of all those things. Like if my active name node is down, so it will move to the secondary name node automatically, right? But there is one issue with this concept, that is secondary name node. So in Hadoop 1.0, active name node, basically when it is working, so secondary name node is used to take the backup of active name node every 1 hour, right? So whatever the configurations that are having at the active name node, we are having just last 1 hour of, like till 1 hour, what was there in active name node, same is having at the secondary name node, right? So let's say at 10 a.m. It took the backup, secondary name node took the backup, and at 10:10 my active name node is down. So secondary name node will take up, but it is only having the data or the screenshot of the active name node till 10 a.m. So last whatever happened in the last 10 minutes at the active name node, secondary name node doesn't have any data, right? So it can lose maximum last 1 hour of data, right? Let's say at 10 a.m. it took the backup, and let's say once it took the backup, at the same point of time my name node is down. So, or let's say at 10:59 a.m. my active name node is down. So that maximum 59 minutes of data you will not be able to access, because the secondary name node is having this snapshot for 10 a.m. So it will think, okay, whatever the 10 a.m. situation is there, it will start from there itself. Understood? So in Hadoop 2.0, they have come up with another concept called standby name node. So what is the standby name node is? So if my active name node is down, so in standby name node, we are having the concept of, the real-time updates. So instead of having this, copy, now in 2.0, it has been given as optional. So secondary name node is optional. If you want, we can have it as a cold copy, but standby name node is a hot backup of my active name node. How it is? Because on top of it, we are also having one called shared, logs file. So whatever happening at my name node, let me give you this. Yeah, this is how it works. Shared edit log, if you see. So whenever my active name node is down, or whatever happening in my active name node, everything is getting shared in this shared edit log file. And that shared edit log file at runtime is being shared by this standby name node. So if it in any case, if my active name node is down, so my standby name node takes over it as active name node, and if within the fraction of seconds it start working. So whatever was happening at the active name node, same information is with there at the standby name node. So we are not going to lose any of the metadata in this case. So at what time active name node left, the standby name node start from there itself, and that's why this active name node secondary name node doesn't have to be there itself. So that's why it has been put at optional in Hadoop 2.0, and that's why it is called as high availability architecture, because we are not losing our data at all. In Hadoop 1.0, for that maximum, for that 1 hour of data we can lost, but here it's all fine, right? We are not losing any data at all. Clear?
Yes.
Yeah, so that's why we call it as high availability architecture. So yeah. So this was we were talking about. So again, master has name node and resource manager, slaves has data nodes, and within data nodes we have node manager and data nodes are there. Again, this is how it works. So client it has to give some sort of has to store something, so it will talk to the name node. If client has to do some sort of processing, it will talk to the resource manager. Then name node will talk to the data nodes, and data nodes will coordinate with the node manager. Likewise, for processing, node manager, resource manager talk to the node manager, and node manager will talk to the data node, because node manager and data node, they are on the same machine, and this name node and resource manager, they are on the same machine, right? So there was one more concept in Hadoop 2.0, which is called as federation architecture. Although this was not used, but it was a tested and tried solution is there. Like in future, if it is going to happen, like we have got that huge clusters are going to be there, where we are not able to process all the metadata from a single name node, then how it will happen? So they have built up this federation architecture. Like instead of having all the metadata on a single name node, we can even divide the name. We can have the concept of multiple name nodes which are having different metadata for different or data sets. Like for financial, we are having one name node. For HR, having name node 2. For healthcare, we are going to have name node 3, and multiple we can add, and all those are connected to the same cluster itself. So whenever we want to process the data for HR, we'll talk to, let's say, name node 2. When we have to process data for financial, we'll talk to name node 1, likewise. So, but because we are having huge, even let's say 1 terabyte of data, metadata is, you can imagine, like if my file size is even in GBs or even terabytes, how much amount of storage it will take to store its metadata? Very even in KBs you will be able to store it, the terabytes of file size metadata, because name node only stores metadata. But yeah, this was built to take account in the future, for the future itself, but it was never because maybe somebody has used, but I don't remember this thing. Like I have never seen that this federation architecture was used by any of the organization, because now the latest are come up with the cloud itself. So there we don't even need those things. This is all being handled by the cloud providers itself. But yeah, this was the tried and tested concept, and everybody was it was not required at all. So this we have already discussed. So this is how basically the the resource manager is going to talk to or going to work with this. So client is asked for reading some sort of file. So within the resource manager itself, we have got the scheduler, and one is applications manager is there. Scheduler is basically schedules all the the jobs and all, and application manager is the one who is looking after all the node managers, giving them the task, and those tasks are going to be processed in the at the node data node itself, and that is being managed by the node manager. So within the node manager itself, we have got the app master. So app master is the one who is taking care of one per task. Like a task can be divided into multiple subtasks, or a job. We can say app master is one per job. We are having one app master for job, but that job can be divided into multiple tasks, right? So that app master is going to manage all the we are going to have app master. So that app master, on how many number of nodes that job is running, that will be taken care by the app master itself. And within each task, we are going to have this container. So container is going to have where my actual processing is going to happen, and so like what is going to be the resource, how much RAM is required, how much memory, like processing, how it is processing, and then finally once everything is done, then this containers app masters are automatically going to be deleted, killed themselves once the job is done. And if one of my, let's say, data node is down, then the same app manager is going to ask this thing to the resource manager, and the resource manager is going to assign the same task to some another node manager. This is how the process happens. So this will in the next session, basically I'm going to explain you in detail. Basically I've just told you the architecture as a whole, but how exactly the reading of the writing and the files is getting happen, I'll show it by making a diagram itself. It will take around some 30 to 40 minutes of time, but then I think whatever, even if you have got some sort of confusions or anything is there, those are going to be cleared. Then if anything is going to be asked from the architecture perspective, you will be able to answer each and everything. Because even if you are going to sit for the interviews, not directly, but yeah, indirectly, these resource manager, node manager, how this Hadoop works, these kind of questions are going to be asked in some organizations, right? Not everyone ask these questions, because nowadays, based on the their requirement itself, and they are going to ask you the questions. But there are certain organizations which are still working on their core concepts, so they generally ask these questions, right? So this is an example of how the cluster. This is a 1100 machine cluster with 88 cores. It means like every one system is having 8 cores, and 300 node cluster with 2400 with 12 petabytes of raw storage, and this is having 3 petabytes of raw storage. So each node is having around 12 terabytes of storage on each commodity hardware. So this is just one typical example of how Facebook used to have different clusters. So now they are having very huge clusters. They are not having just around 1100 or 300 node clusters. They are having around even their cluster size in few thousands of nodes, and even the storage has been increased, and they have also increased their cores also. Yeah, so yeah, well, I think today we can just stop it here, because now few things I'll show you in next session of how we are going to use these different modes also. But from next class onwards, once we are done with the cluster, we'll be moving to the Spark side now, right? This was just to give you a background of how the things works in Hadoop and all. So once we are done with that, then mainly we'll be focusing on the Spark side. So once the Spark will be done, then we'll probably then start working doing some hands-on by creating the account on the Azure portal itself. And we'll be doing Azure Databricks, right? So from there onwards, then understanding the Azure services, understanding the Databricks side, that is going to be the thing that we are doing on daily basis, right? So that is going to be the actual thing that we have to do. But whatever we have did, or even in the next session, that will mainly going to cover the the basics of what has been done so far, right? Any questions, any queries so far? Please let me know. I think we can stop it here today. Will that be okay?
Yeah, it's okay.
Okay.
That's fine.
Yeah, I'll share